Hello guys, this is what we are going to have as a result. This is a simple smoke simulation, and we are sourcing the smoke from a sphere, and as you can see, our force follows the curve, and the smoke also twists around our curve. If you see here, from this angle, for example, it twists around here. So if you see here, it is twisting and following, and it's attracted to our curve. And we are going to add a lot of controls here to the simulation, and we are going to create a force like this or a field like this. So this is just a simple smoke simulation, and we created this example before, and we have our curve object here. This is just a curve node, and we drew this curve here, okay? And we are going to create this from scratch. Surely we are going to use the velocity update input here because we are affecting our velocity field. So we are firstly going to create a SOP guide node, and this node here is just a SOP network, okay? But this SOP network is not going to be executed, okay, or calculated in our simulation unless you press on show guide geometry, or when you call anything that happens inside it, okay? So this node here just has the option of show guide geometry, okay? And this option here is here, and this option is very great. We can show the thing that inside our SOP, okay, without calculating it every time, and it's calculated also when you call the nodes that inside it. And this is going to be more clear when we deal with it, okay? So if we enter here, here we are in a SOP network, so you have all of the nodes that you can use in the SOP. For example, you have the poly, extrude, you have all of the nodes that you are using in SOP networks. And this is great in Houdini. You can use SOPs inside DOPs. You can use any context inside any context. Okay? So the first thing that we are going to do, we are going to have an object merge, okay? And in this object merge, we are going to reference our curve. So now we are getting our curve from the SOPs, okay? Then after we do this, we are going to resample our curve. So now we are adding points to our curve every length here. So every 0.1 of length, we are going to add a point. So if we show our points, they are here. Okay, I don't know why they are small, very small like this, but here we have our points. And we can make the length less, and it's going to add more points. Okay, but we are going to stick to 0.1 now. So now we have our curve resampled. What we are going to do after this, we are going to create an attribute, wrangle, okay, and this attribute wrangle, we are going to use it to create an attribute called length scale, and I'm going to tell you what this attribute does, because this needs more clarification. So if we create another scene here, okay, if we have our curve like this, for example, let's draw a better curve like this, for example, and we have points along the curve. By default, the points are ordered along the curve. So this is point 1, this is point 2, 3, 4, 5, 6, 7. Okay, so now we have 7 points, but actually the numbering starts in Houdini from 0. So the first point will have the number 0. Okay, because this is going to have to be this is going to have significance. Okay, so we have in Houdini an attribute called pt num, which represents the number of the point. Okay, 0, 1, 2, 3, and blah blah blah. And we have another attribute called num pt, which represents the whole number of points. So we here have 7 points. Okay, so to create a length scale attribute that represents the length or the distance between this point and the end of the curve. So for example, here we may have a length between this point here, or a distance between this point number 1 and the end of the curve. Here we can have a distance of 0.5, but here in this point number 2, the whole length is bigger to the end of the curve. You have all of this length. So here it may be 1, and here we have this length towards the end of the curve. It may be 2 or anything. Okay, so this is going to be our length scale. To do this, we can just divide our point number over the number of points minus 1. Okay, so let's take this intuitively. Okay, for the point number 1, for example, we will have a length scale of 1 over, we have here 8 points from 0 to 7, we have 8 points, so sorry, 8 minus 1 is going to be 7, and for the point number 2, it's going to be 2 over 7, for the point number 3, 3 over 7, 4 over 7, okay, 5 over 7, 6 over 7, then in the last point it's going to be 7 over 7, and it's going to be 1. And for the point number 0, it's going to be 0 over 7, which is going to be 0. So if you now notice here, we are having now an attribute that comes from 0 and increasing here to 1 over 7, 2 over 7, 3 over 7 until we reach 1. So now we have an attribute from 0 to 1, which represents intuitively the length from the point to the end of the curve. Of course, these numbers are not the actual length, but they are numbers increasing from 0 to 1, and they increase more from 0 to 1 depending on how far the point is from the end of the curve. So the last point will have a length scale of 1, and the first point is going to have a length scale of 0, and we're going to increase from 0 to 1, okay, until we reach the end of the curve. And this attribute is going to be very, very useful. We can manipulate our forces depending on how far this point here is going to be from the how far the point is from the end of the curve. Okay, so we can manipulate our force along the curve from the first or from the end, from one end of the curve to the last point at the other end by this length scale. Okay, we can, for example, choose the points at the end of the curve to have larger force or a bigger amount of force, and the points at the beginning, for example, we can choose to make the force smaller at these points. So this is going to be great. And we are going to do this inside of I'm sorry, we're here having the sub guide here. We can define our length scale attribute, and this is going to be our point number divided by the number of points minus 1. Okay, and because the point number and the number of points are integer attributes and our length scale is a float, so the integer attributes is just a number without fractions, and our length scale is a float, so it will have fractions. So we need to convert the integer attributes into float by the float function. Okay, the float here, we can type just float like this. And if we now see here, I don't know why it's not working. Sorry, the number of points shouldn't have S here. It's going to be like this. So you have now your length scale. You here have the point 0, and it's just 0 length scale. And the point here, the last point here, will have a length scale of 1, and you have increasing values from 0 to 1. So this is really great. You have now your length scale. So now after we do this, we want to create our tangential vectors. So to do this, we should create a node called polyframe. Okay, and this node, if we visualize the normals now, it computes the normals to be like this, because we are choosing the normal name here and putting the n, which is the normal. But we can disable this, and we here have the tangent name, which represents the tangential vector. We can here, instead of tangent u, if you middle click, you'll have this tangent u. We want to store the tangential vectors into our normals because they are more easier to access. Okay, so if we do this, if we put the normals, we here have our normals tangential to our curve here, like this. Okay, if you see here, yeah, they are tangential from upwards downwards. Okay, now we want to create the volume that bounds our simulation. So we are going to create a bound node. Okay, this node takes your geometry and generates a bounding box that bounds this geometry. So here we have a bounding box here bounding our curve, and now we want to create our volume, so we can create a volume node, and this volume node here creates a volume. So if we choose here vector volume and call it, for example, velocity, okay, we middle click now, it creates a Houdini native volume. Here a vector vel.x, vel.y, vel.z. It's just a vector volume. Okay, and maybe we can give it a value, any value. So you'll see your volume here in the viewport, but we don't want this. We want it to be 0. And you can connect your bound node to this volume. So here we can now see our volume. If we see here our bounding box and our volume, I think there is a problem maybe in my viewport or something. Set an initial value of 1, for example. Yeah, it's creating our volume here. Okay, but I don't know why it's not visualizing in our viewport when it's 0. Anyway, we can now in the uniform sampling here, which defines the resolution of our volume, we can set it to by size, and this is the division size. Okay, now we are creating our velocity volume and it's empty now. After we do this, we can create our volume VOP node, and we are going to connect our volume to this volume VOP node. And if you enter here, this volume VOP is just like the gas field VOP. You can manipulate your volumes. You can bind them by a bind node, and this is the great thing inside this node. Now we will connect our curve to the second input of our volume VOP, and this is because we want to use the voxels as the position of the point cloud, and we want to search within a search radius in the curve points or the curve geometry, like we said before. So here in the volume VOP, we can disconnect this. We have here the position of the voxel, okay, and we can access our fields or volumes with bind nodes like we did in the gas field VOP. Okay, so now we are going to create our point cloud. So if you type point cloud, you'll have a bunch of nodes here, a bunch of point cloud nodes. We have here the point cloud open, the point cloud filter, and the point cloud num found. These nodes that we are going to use now. So let me firstly add my PC open or the point cloud open. And here in this point cloud open, you have the position, which we will connect here, the position of the voxels, and you have the file here or the point cloud texture here, which refers to the geometry that we want to search into. So if we connect this now to the op input 2, which is this here, which is our curve, we can now search through our curve, and we here have the search radius. Okay, and we have the number of points that we are going to grab within the search radius, and surely we are going to average the attribute that comes from these points if we use the PC filter node. So what I'm going to do now, I'm going to promote the radius here, because this is going to be the radius of search that the user can control, and we are going to rename it to max radius, maximum radius, and the default I'm going to set it to 1. Okay, now we have our maximum radius. After that, I'm going to add my PC filter node. Okay, In this PC filter node here, you can grab an attribute here. You can type the attribute in the channel, okay, and select the signature of the attribute. Is it a float, an integer, a vector, and anything? So we now are going to grab our length scale of the curve. If you remember, the length scale was an attribute from 0 to 1, depending on how far the point from the end of the curve. So we are going to grab this length scale. And what we are going to do now, we are going to control our radius based on this length scale. So we can give the user the ability to control the radius of, or the search radius of the point clouds based on this length scale. As we did before, we created ramps before. Let's rename this first to DC filter length scale. If we add now a ramp parameter, and I think you are familiar now with the ramps, we're going to call it spline ramp, and we can call it a long length radius ramp. And we can rename it here radius along curve length, for example. Okay, and this point here is going to represent the end of the curve, okay, where the length scale is 0, and this point is going to represent the other end where the length scale is going to be 1. And now we can multiply this here. We can multiply our radius, okay, by this length scale. So now we are just manipulating our radius as we did a lot before by ramps in the masking videos. We are manipulating our radius, okay, along the length of the curve, and this is the usefulness of our length scale. So now we have our ramp here controlling our radius. So I'm going to make our ramp one like this, okay, because I don't want our ramp to change anything in my simulation. For now, the user wants to change the radius, but I want a uniform radius. Okay, so now we have this multiply. We can create a null just here. And this is going to be all our local radius. Okay, this is our local radius here. Now we can use this manipulated local radius here to open a new point cloud. Okay, so now instead of using this radius here, we are going to use the radius that we already edited by the length scale attribute to search for the points in the curve. So we are going to connect the same things that we connected in this first point cloud, but now we are using a different radius that the user can control by the length scale. And now we can filter two attributes. We can filter the position of the points of the curve, and if you remember, we used this we are going to use this position to create our suction force and our cross product that is going to generate our twisting force. Okay, and we are going also to use another PC filter to filter our normals. Okay, so now what we are going to do, we are going to create our forces in the way that we already discussed. Let's firstly create our along force. As we said, the normals are the tangential vectors, but we want to negate them to get the right direction. And this is going to be our along force. We are going to normalize it because we want a length of 1, okay? Then we are going now to create our twisting force, or firstly, let's create our suction force. As we said, we are going to subtract the position of the points of the curve minus the position of the voxels, and this is going to give me a vector from the voxels to our curve, and we already discussed this, so this is going to be my suction force. We are going to normalize it. Okay. Then lastly, we are going, want to get rid of this. We are going to create our twisting force using a cross product node. Okay. Use a cross product node here and do a cross product between the normals and our subtracted vector here, and we already discussed this. This is going to be my twisting force. So now we have 3 forces. We have our along force, we have our twisting force, we have our suction force. We can add the 3 forces together. Okay, then we are going to add a bind export now to export these as our velocity volume that we already created. So now you'll start having something here in the viewport. If we go outside now, we can visualize this volume using a volume trail, as we already did before, I think. So to do this, we are going to use a node called volume slice, and this is going to give me a slice here along my volume, and we can use a volume trail node. We can connect this to the points to trail, and here the velocity volumes. And here we can, in the velocity volumes, we can choose our vel.x here. Let me unshow the points and the normals. So if you see now, we are having something here. Okay. So I don't want to calculate the force in the whole volume. I just want to calculate the forces in the voxels that found already points from the curve in this point cloud. Okay, So if this point cloud found points of the curve, then we are going to calculate all of these forces. Otherwise, we don't want all of these forces to be calculated in the other voxel. So we are just going to calculate of the forces in the voxels within the search radius. So to do this, we are going to use the other node that is called point cloud numFound. So this node returns the number of points that are found by the point cloud, and if there is no points found in the voxels that are beyond our search radius, it's going to return -1. So we can now compare the number of the points. So if it finds points, the number is going to be greater than 0. So if we find points, okay, or the number of found points are greater than 0, we are going now to create an if block like we did a lot of times. So this is our if block. We can now output our force here if the condition is true, but if the condition is false, we can now create bind node, okay, and bind our velocity vector. I think Houdini